So if we have 4 areas of electron density around the central atom, we already decided that this is going to give us a tetrahedral electron geometry. Well, that means that we need 4 bonding orbitals. So we're going to take 4 atomic orbitals and hybridize them together. So our 4 atomic orbitals are going to be s and 3p orbitals. So we're going to call this sp3 to show the atomic orbitals that are coming into play here. So sp3 is 4 orbitals being hybridized together. And then when we take these 4 orbitals, s is going to be a single sign, and each p is going to be a positive and negative sign. So when we hybridize them together, we're going to get one big lobe and a small lobe for each of these. They're going to be pointing in different orientations in space. After we do it mathematically, we will get our linear combination of atomic orbitals to give us the sp3 hybridization, which will also give us our tetrahedral geometry. So in this case, the big lobe of each of these hybrid orbitals is going to be our bonding lobe. So that'll give us our greatest overlap of electron density with the adjacent atoms. So we're going to end up with 4 hybrid lobes, each pointing in a tetrahedral geometry orientation. The other thing that happens that when we hybridize our orbitals together, each of the atomic orbitals is associated with a specific energy. When we hybridize them together, we're going to average these energies together and come out with an average energy. So the energy of all the hybrid orbitals will equal the average energy of the 4 orbitals going into it. If we have 3 areas of electron density, we already know that it's a trigonal planar arrangement, but that means that we also need 3 bonding orbitals, so 3 hybrid orbitals. So we're going to take a s and 2p orbitals and hybridize them together. So we're going to get what's called sp2 hybridization. So we're going to have our s, which is a single phase, our 2 p's, which have 2 lobes each. If you're going to hybridize them together, we're going to end up with 3 hybrid orbitals, each with a large lobe and a small lobe. The large lobes are going to be oriented in space to give us a trigonal planar orientation, and the large lobes are going to be the overlap lobes for our bonds. And again, when we are hybridizing, so we're going to take the orbitals that we're hybridizing and we're going to average them together. This, of course, means that we're going to have one p orbital that is unhybridized. This one p orbital is available for pi bonding. But we're going to have 3 hybrid orbitals that are average of the 3 orbitals forming those hybrids. If we have 2 areas of electron density, we need 2 bonding orbitals, so we're going to take one s and one p and hybridize them together. So this would be called sp hybrid orbital. So s is a single lobe of one phase, and p is 2 lobes of separate phases. When we hybridize them together, we're going to get 2 orbitals, each with 2 lobes, one big lobe and one small lobe, and these lobes are going to be pointed in opposite directions 180 degrees apart, creating the linear structure that we find for sp hybrid orbitals. Those were for the octet-obeying structures. Now to exceed the octet, so if we're going to have 10 electrons, so 5 areas of electron density, we're going to need 5 bonding orbitals. So we're going to take our s and our 3p. That gives us our 4 orbitals that obey the octet. So to exceed the octet, we have to pull in a d orbital. So that'll give us a d sp3 hybridization. And The 5 orbitals that blend together will give us 5 orbitals coming out. These 5 orbitals give us the trigonal bipyramidal geometry. To get the 6 Aries electron density for octahedral structure, we're going to have to pull in 6 atomic orbitals. So that'll be the S, the 3p, and we have to pull in 2 d orbitals. So this will be d2 sp3 hybridization. This is for our 6 Aries electron density, which means an octahedral structure. And it'll also include the square planar and square pyramidal structures, which are based on the octahedral electron geometry. So we're pulling our 6 orbitals, blending them together, and we get 6 orbitals out. Those 6 orbitals will have the geometry of the octahedral structure. So the hybrid orbitals, this corresponds to a electron geometry. So SP is going to be linear electron geometry, bond angle 180 degrees. SP2 is trigonal planar electron geometry, bond angle of 120 degrees. SP3 for Aries electron density, that will be tetrahedral with a bond angle of 109.5 degrees. A DSP3, this is 5 Aries electron density, so that's trigonal bipyramidal. Bond angles 90, 120, and 180. Then octahedral electron geometry has 6 Aries electron density, which gives us a D2 sp3, total 6 orbitals, and its bond angle will be 90 degrees. In molecules with conjugated bonds, that means bonds that are double bonds that are separated by single bonds, and structures with resonance structures. These showing that the bonds can move around, the double bonds can move around, and showing also that we have delocalized pi bonding. And delocalized pi bonding can run from 2 adjacent bonds to many adjacent bonds. So the example here would be a benzene ring. When you draw this benzene ring, we would show 3 double bonds separated by 3 single bonds. Well, that means that there's a unhybridized p orbital in every atom, every carbon atom, and we can resonate between double and single bonds with 2 different configurations. But what it also really means that this 6 pi bonds, p orbitals, can overlap to form a decentralized pi bond around the whole ring. This creates additional stability. So the more delocalized bonding that we can get, the more stable the molecule becomes. So for this benzene molecule, we can have 2 resonance structures of alternating single and double bonds, or we can have one structure here with a delocalized pi bond around the whole ring. And this is the more accurate description of the actual molecule. So in this valence bond theory, we are sharing 1, 2, or 3 pairs of electrons in each bond. One pair is going to be directly on the axis between the 2 nuclei, and this is the sigma bond. These sigma bonds we form from hybrid orbitals, a linear combination of the atomic orbitals, SPD, which gives us new hybrid orbitals with the bond angles and geometries that we find in molecules. If we have a double bond or triple bond, the second or third pair of electrons is in a pi bond, and the electron density is above and below the bond axis, not directly on the bond axis. And then if we have resonance structures where the double bonds can move around, then we can actually have a extended pi bond over those double bond locations. So this theory is good. It qualitatively describes its ability to covalent bond. It describes the geometries we get from the valence shell electron pair repulsion model with hybridization. So hybridization allows us to get the geometries and bond angles out of it. But it doesn't describe everything that we observe in molecules, such as paramagnetism and diamagnetism. So we're going to have another theory to describe that.